Hey Veronica.
Hi, Carl. How's it going?
Good. So do you want me to share like to start, or you have your own little thing at the beginning?
If you want to go ahead and put your title slide up, just
Okay.
so we're ready to roll. Once we let quite a few more people filter in here, I will go ahead
Switch it.
and begin with the script.
Okay. Sounds good.
Thank you for joining us today, everyone. My name is Veronica Wild, and I'm going to be the host for today's webinar before I pass it over to Carl. We're lucky to have Carl Talsma presenting on identifying critical pathways for CO2 pipeline networks. Carl will delve into the challenges of pipeline routing, a significant barrier to effective carbon capture and sequestration. He'll introduce a comprehensive net framework for evaluating multiple pipeline pathways, considering both stakeholder priorities and public perception to build more resilient networks. Please note that this webinar is being recorded and will be available for your review afterwards. With that, I will go ahead and pass it over to Carl Talsma. Carl, the floor is yours.
Great, thanks, Veronica. Yeah, the basic gist of this presentation is going to be centered around CO2 pipeline routing, as the title suggests. We have SimCCS is our big piece of software that we use for modeling carbon capture and sequestration infrastructure buildouts. So it's which sources are you using, which sinks are you choosing, and then cost map, which is the piece of this that we're going to focus on, is the transport part of that suite of software. So it handles the pipeline routing and the pipeline costs. And pipeline routing kind of represents this big problem for these CCS projects in terms of public perception, because it's the most public interfacing part of these projects, right? No one cares too much if you're capturing CO2 off a smokestack, but if you're routing a pipeline through your property, people are going to start to care, and kind of mitigating that impact or presenting alternatives to routing options is a useful tool in making sure that these infrastructure projects succeed. So typically our software, what it would do is it would produce an optimal path. And kind of the motivation behind this is, instead of one path, what we found is when we presented the quote unquote optimal path to people, is that the reality on the ground was not the same as, the data inside of our software. There's pieces that our software is going to miss, and can't, it can't tell you whether a landowner is going to object to this pipeline or not. So kind of the motivation behind this was trying to find a way which we could still utilize our software, but kind of come up with a range of realistic scenarios to choose from. So I'm going to run through how cost map works really quickly. It's going to be pretty surface level for the method section of this. But the basics of what it does is it compiles a lot of different spatial data, and it's going to tell us both whether those data features will increase the cost of a pipeline or decrease the cost of a pipeline, or if they are places we want to route towards or route away from. So you can see kind of some of the data that we use along the top there. We use things like topography, federal land ownership, railways, rivers, roads, land use, existing pipelines, population density. And we use all of those. We end up weighting each of those features within each of those data sets. And we say, is this a place we want to route to? Is it a place we want to route away from? And we produce both a cost surface and a routing surface. The cost surface is just exactly how much is it going to cost to build a pipeline here. And the routing surface is going to incorporate things beyond cost, like population density, like environmentally protected areas, that, it wouldn't necessarily cost more to put a pipeline there, but it might not be a place we want to put a pipeline. So that's kind of what cost map does. And then we end up feeding both the routing surface and the cost surface to SimCCS. And SimCCS uses a shortest path algorithm called Dijkstra's algorithm, which will find the optimal route based on the routing weights we have assigned to go from source to sink. So you can kind of see how it works. This is the best representation of Dijkstra's algorithm that I've been able to find. Is the algorithm will radiate outwards at equal lengths. So it'll, explore all of the lengths equal to 10, it's going 10 kilometers, and it'll explore all the paths that go 10 kilometers, and then it'll go 11 kilometers. And it kind of goes out and out and out, and eventually it finds the sink, and you can see it's going to find the shortest path there. For us, it depends on the routing weights. So we route things depending on whether we want a pipeline to go there. So, a length, crossing a river might incur a greater length for the algorithm than just going along, a flat surface. Um, and the route that the algorithm finds is really dependent on the underlying surface. So it really dependent on how well we've weighted those data features I was talking about in the last slide. Um, and there's stuff that we just aren't going to be able to get in the data, right? We're not going to know which landowners are going to be amenable to pipelines and which aren't. We're not going to know kind of the larger scale community benefits or community impacts that a pipeline might have. And then there's also uncertainty in the data itself. So you can imagine just looking at this, even this example, the shortest path ends up going around the bottom of this obstacle. You can imagine, the path that goes up and above the obstacle is not that much longer, but it is very spatially different. And if you imagine this in the context of pipeline routing, there might be a landowner along this shortest path that says, yeah, no, no way, I don't want a pipeline here. And this slightly longer path might actually be more feasible and cause less conflict than the actual shortest one. And it's not incurring that much more of a cost. So I thought that was interesting. And it was a question that we didn't really know, like how many, if we allow for like 2% longer pipelines, how many different paths could we make? Are they very different? Are they slightly different? What would that look like? And that kind of led us to these K shortest path algorithms. Um, so you can see there's a pretty analogous problem with road networks, right? Everybody uses Google Maps and you type in your destination and it gives you multiple routes. So it's a problem that already existed, and I could not find within the context of pipeline routing people using these algorithms. And we kind of started with the top panel here, these K shortest path algorithms that give you an exact solution. So it will give you the 100 shortest paths exactly solved optimally. And that took a really long time to produce. It was really computationally intensive. And you can see you would kind of get these paths that you don't care about, like going back to the road analogy, if the algorithm routes me a block away and just returns to the normal path, that's not super useful to me. And so what that led us to was this group of algorithms called K shortest paths with limited overlap, which is exactly what it sounds like. It's limiting the overlap between paths. So you see this ESX algorithm was what we ended up using. Is you set this overlap threshold. You're saying, I'm only going to allow you to overlap 90% of the time or 50% of the time. And you get these much larger deviations in the path that are actually kind of more interesting to consider for both road networks and pipeline networks. And the nice thing about ESX algorithm is it really reduced the computationally intensive part of it. We can run it super fast. We can produce a bunch of different routes. They're not exact, so we're not exactly getting the 100 shortest routes, but they're different. They're different. They might be longer than we would get if we did the 100 shortest paths, but I think they present better options, for the purpose of pipeline routing. And the way most of these algorithms work is we have our network, right? We run the shortest path algorithm, and then you just clip off a branch within our shortest path. So we're saying, you can't use this small piece of the network anymore, and then you rerun the algorithm, and you kind of continue to do that until you get a bunch of different paths. Where the kind of details come in is how are you choosing which branches to cut off, and how are you limiting overlap in between the paths. I'm not going to get into that ton of the minutia there, but there's a bunch of different algorithms. We chose ESX because it's fast, basically. And this is going to run through how this happens again, kind of explaining what I just said again. So we have our optimal path. We find that running Dijkstra's algorithm. And you can think of this path as a bunch of nodes and branches. So we've got all these nodes and branches along the path. We choose what we call the pruning node based on our priority queue. So there's this priority queue of nodes, like which ones do you want to eliminate first? We just chose our highest routing weight. So the place we didn't want to route toward, the least amenable place for routing along the path that actually ended up getting chosen. So we clip off the branch there, and then we run the algorithm again, the Dijkstra's algorithm, and we find an alternate path. And the alternate path might not necessarily branch off at the pruning node. It might branch off much earlier. There might be a shorter path that kind of doesn't utilize the path that was made before, right? But that's just the basics of how it works. Is you're running it over and over again. You're clipping out parts of your network, and really that's all you need to know. Again, there's more minutiae about how you're limiting overlap. You don't want to clip out all the nodes surrounding your source, right? So you can't get at it. There's stuff in the algorithm to handle that. But basically, it's just continuously running, continuously clipping is how it works. So now we're going to show you what it produces a little bit. So this first test case is just as simple as we could make it. It's one source and one sink. The source is the Labadie coal plant, and the sink is a point in the Mount Simon sandstone in Illinois. This is, I wanted a realistic scenario, but not something that would actually happen in real life, right? The Labadie coal plant is due to be decommissioned. Like it's not, no one's going to build this pipeline. I kind of wanted it far enough removed from reality, but close enough to where we're able to evaluate that algorithm. And basically we ran this and we just changed the number of paths we were outputting and then the overlap parameter, which is called theta. Basically, how much overlap are we allowing? So we can see the first outputs here. So we're allowing 90% overlap and we're outputting 25 paths. And I'm going to decrease the amount of overlap we're allowing as we go here. So our sink is up here in the northeast. This is the Mount Simon Sandstone Formation in Illinois. And then down here is the Labadie coal plant. Some of the major features of the land surface is we've got this big St. Louis metro area that we have to route through. That's kind of the major obstacle. And we're also crossing both the Missouri and the Mississippi rivers. And then we have this big straight section that runs east to west is an existing pipeline that the algorithm likes to use. And then running north and south is also an existing pipeline that the algorithm likes to use there. The gold here is the optimal path. This is what we would normally find if we just ran Dijkstra's. And then this kind of the red to purple paths are the alternate paths that the ESX algorithm is producing. And you can kind of see, right, initially, if we're allowing a lot of overlap, it kind of, all of the alternate routing paths focus around kind of where it crosses the Mississippi River and where it crosses the Missouri River. We're getting a lot of different paths there, which if you're focusing on those areas, it might be super useful. If you zoom in super close and you're hyper focused on the details, right? We also get this pretty different path that kind of cuts off the right angle of the existing pipelines, which is interesting. So the algorithm is saying basically, if we reduce the length of the pipeline, it's pretty similar to actually using the pipeline corridor based on how we've weighted it. Normally, we want to use existing pipeline corridors because it makes it easier to secure right-of-ways, right? And this is saying, based on how we've weighted it, you could cut off a significant length of pipeline. That's going to equal, the savings that we're getting from using the corridor. And as we allow less overlap, you can see we get more deviations to the paths. We're getting much farther deviations to the west. We can continue to decrease. So this is allowing 60% overlap. We get more paths. 40% overlap looks pretty similar. And then I just want to draw your attention to these 3 points. So this is kind of the 3 major points where it's routing through that St. Louis metro area. And you can kind of see that the pathways kind of branch out and then come back together and then branch out again. So we've got kind of these 3 choke points where we're routing through the St. Louis metro area. Um, our optimal path here kind of utilizes the Missouri River, where there's less development along the river to route the pipeline. And then we get these two alternate pathways further west, where one is going pretty far west and then kind of cuts through some of the development, and then one goes very far west, kind of routes all the way around the St. Louis metro. And that middle one, actually, there's another existing pipeline there that utilizes. So I think it's interesting. I think, this is something that we could analyze further. It's kind of telling us where to focus on the details to get through St. Louis, right? You've got these three options. One is utilizing a river, which, it does a good job of getting through the developed area, but you might not want a large length of pipeline along a river. If there's a leak, it could seep into the river there. And it's not that damaging, but it would turn the water anoxic. Might not be something you want. But how does that compare to these other routing choices of going through these populated areas, or building a much larger length of pipeline? You begin to develop this framework for kind of analyzing which of these options is best. What are the cost benefit analysis of choosing these three options, which is something we didn't have before, right? So these next slides, I'm continuing to allow this overlap. We're getting much different routes. We get this big one that goes far out west. An interesting thing is that when I really decrease the amount of overlap, some of those routes disappear. I think that is because we're no longer letting those paths use this pipeline right of way. So it just doesn't want to go super far west if it can't use the pipeline, right? So we end up getting these parallel paths kind of that are more direct, and using the right of ways less, which is probably something we want to avoid. So this is kind of a minute detail for us, but it gives us an idea of where we want to set these parameters. This is what all those things look like together. You can see kind of as we allow more overlap, we get more diverse options. Something that also gives us more diverse options is just outputting more routes. So this right column here, we're outputting 100 paths instead of 25 paths. And we do get kind of similar results. We see that big western path show up again. So the way I have come to think of this is adjusting theta gives us, how local do we want these deviations to be? When I had 90%, most of the deviations were very attuned to those small details of crossing the river, right? But if we decrease theta too much, we kind of get we start ignoring some of the features that we want to be in there. And I think the coolest part of the results here, is that we're able to identify those key choke points of routing around our major obstacles, right? And we can begin to think about those in a more sophisticated way. We can, give this to a developer and say, these are the key areas that you want to focus on, and we've got these multiple options that you might want to consider, which is something we couldn't do before. I'm going to move on to my next test case. So basically, this was just testing the algorithm out and seeing kind of what it was giving us. The next test case, I wanted to consider how routing might change a broader CCS infrastructure project where you're getting multiple sources and multiple sinks. What does considering different routes there do to the broader 1,000-foot view of the project? And we ended up using the Heartland Greenway project as a test case for this. For those of you who don't know, Heartland Greenway was a big CCS project in Iowa and the surrounding states, and it captured ethanol and transported it to Illinois in the same formation I was talking about in the last test case. And it was canceled in 2023 in large degree because of public backlash to the use of eminent domain, and just people basically not wanting pipelines in their backyard or in their communities. And I don't want to make too many judgment statements about the project, because the real reason I used this for a test case is because they were capturing mostly ethanol, which is very, very cheap to capture, and they're able to transport it a much longer distance. So trading off the cost savings that they're getting for capturing ethanol with these big transport costs, which, I kind of wanted larger transport costs to see how, um, you know, changes in the transport costs would impact greater changes in the overall network. So that was the real reason I was using this as a test case, but there's an added benefit of like, the pipeline routing didn't really work out here. And that's why we're using this. There's a bunch of press about it. I think probably anyone who's in CCS has heard about this project. So, but again, like the ratio of the transport cost to the capture cost was the reason I was using it here. So what we did was this is the network structure. So we've got one sink down in the Mount Simon sandstone again, and we've got 33 CO2 sources, most of which are ethanol. You can see there's about 11 megatons per year of CO2 total. And what we did was we created this candidate network. And normally what we would do is we would create one path between, you make these Delaunay triangles and you produce one path between sources and one path between sinks. And that's kind of the way we've done things in the past. What I did is instead of producing one path, I produced 10 paths. So you can see down, if we look down at the sink here in the southeast, this link here in between this closest source and the sink, instead of one path, I'm producing 10 paths there. And then I'm doing that for each of the links between all of these sources, right? So we've got much more paths, much more optionality in how we're routing the pipeline. And this is what we fed to SimCCS, which chooses which sources to capture and where to route the CO2. So we actually did this, we had 6 separate scenarios where we were changing the volume of CO2 we were using and also the amount of overlap we were allowing. I'm only going to show one of those scenarios, so that's represented in this figure on the right. And for each scenario, we ran SimCCS 10 times. So what we did was we would, between each node, we will choose one path randomly out of those 10. And we did that independently for each node pair, right? And then we ran SimCCS. So we've got 10 simulations of SimCCS, and they're all overlapping each other here. So you can see on the right, the pink would be our normal optimal routing scenario if we were just using one path, just the optimal path. And then all these green lines are the pipeline routes for the other 10, the 10 random iterations where we're choosing different paths. So just the goal here was, if we're allowing for alternate paths, how does that change the network? And it ends up changing it quite a bit. Like, we're getting very different spatial results. You can see like this, the pipeline running kind of northwest to southeast here changes a lot. There's the optimal route that's kind of more northeast, and then it changes entirely to this different route that kind of runs parallel to it. To me, that's a big change in there's not a lot of overlap between those two pipeline networks, right? And we actually see also the sources toggling on and off. So the pie charts where the sources are represent the mean capture percentage across all 10 scenarios. So you can see like the optimal path chooses this source that's farthest north when we're using the optimal path, but it doesn't choose kind of these sources that are further west, which is interesting, and you can kind of see, if I own a, CO2 well and I'm looking for, CO2 emissions people to partner with, and regionally, it's kind of interesting that, these sources that are closest don't always capture when we're running these simulations, right? And kind of some of these sources that are further north are capturing 100%. So what if some of our pipeline routes don't work out, and we have to route differently? You end up getting very different solutions, which I thought was super interesting. And yeah, if I'm someone who's trying to partner with CO2 emitters, I might choose the sources here that are capturing 100% of the time. Yeah, I kind of explained this one, but another interesting point is how different are the costs here. So when we're allowing for these alternate routes, the costs to me aren't that different. It's only 4.5 to 6.2% costlier than the optimal solution. And then the pipeline length kind of scales similarly to that. So as it gets longer, it gets costlier, right? So that to me is not that different. And that's using random variation, right? If we were to choose all of the second choice paths, that the cost would be much closer, right? So for a small amount of additional cost, we're actually getting very, very different networks, which again is pretty interesting. This is looking at the different pipeline links. So, right, when I'm talking about links, I'm talking about, this source is linked to this sink. We've got a pipeline running between it. How often does that link deploy? And again, what we see is that, you know, to me, a surprising percentage of these links deploy 100%. It's pretty small compared to what I would have thought going in. We're only getting about 15 to maybe 35% of links deploying 100% of the time. So yeah, again, it's just reinforcing that these networks are pretty different for, relatively modest changes in the cost. Yeah, again, just to wrap this scenario up, for increased costs, we're getting a very different network, which is interesting. It's an interesting thing that this test case told us. But one thing that I wanted to answer going in was like, where are the critical points of routing for a network? Like, where is the most important part where we have to like nail the routing right? And like, where are all of these networks sharing the same corridor? And at first I thought it was like just where they're overlapping, right? Where all these networks overlap is going to be the most important point. What ends up happening is where the networks overlap with each other is often kind of it's where the routing weights are pretty low because of the way we set up the priority queue. We're eliminating the high nodes, and that's often where the deviations happen. And where the weights are lower, it's like, we could get a pretty similar pipeline network if we just moved it, 500 feet. It's the land surface is pretty similar. And for this problem, it's the topography is not very different. The land is pretty similar throughout the whole region. So there's not a lot of variability in the land surface stress. And I wanted to, yeah, try and figure out like where is the routing of the network really integral and someplace like we have to go. What's a choke point? And how we kind of formulated that was using what we call the pipeline importance index, which is basically just the product of, you were just multiplying the pipeline density, like how often are these networks overlapping with the routing weight, like where is it overlapping a lot, but it also has a high routing weight. So we're basically multiplying those together and normalizing so they're weighted equally. And that's what we kind of formulated to get an idea of this. And when we run it, we do get some interesting results. So this is the far north portion of that pipeline network that I was showing. And you can see where the importance index is high is where this is more yellow. And we can start to get these places to pop out. And it's kind of immediately obvious why those places are popping out. For this portion here that's in the middle of the screen, there's just a ton of surface water there. And it's finding this one path that routes through, and it's not finding alternate paths. And right, it's really the only option for routing through here. Whereas as you continue kind of further up the network, it's finding alternate routes to route through the water, all these lakes. But for this portion down here, it can't find any other route. Like it really has to go there. So again, we're identifying a choke point where routing is really important. And similarly, if we move kind of to this other scenario where we're also seeing high values, we're starting to get into these population centers, into kind of more developed areas. Again, there's more lakes here also, but it's only really finding this one route to get through all of this. Even where the routing weight is high, the pipeline network is kind of forced to use these corridors. So this is something that I think is really cool, and something we kind of added on late when we were doing this analysis is how do we identify what the really integral places to route these pipelines are. Um, so that's kind of my last result here. We're just going to wrap it up. But basically, the key takeaways here are we're able to produce big changes in routing at relatively small costs. Like those things are not synonymous. We can create very different networks that really aren't that different if you're paying for it. Another key take home is that we're able to identify these choke point areas, both qualitative, right, in that first test case, and quantitatively using the metric that we derived there. Another takeaway is that changes to pipeline routes can have big impacts on the structure of the network as we see those sources toggling on and off, right? There's kind of these big impacts that are happening just with these small changes in routing. If we're spending 5% more on a pipeline over here, that might totally change how we're constructing our network. And then the last takeaway is identifying more flexible routing options can help us in um, kind of having a better understanding of the costs and benefits of these routes, right? We can analyze these more in detail. We can try and figure out, what routes might be better for the public good, which routes might not be actually be options, even though our software is outputting them. And how do we build these networks so they impact people the least? Yeah, so that's my presentation. Happy to take questions. That's kind of the end.
Thank you, Carl, for sharing your insights and your expertise with us today. If anybody does have questions for Carl, please feel free to drop them into the chat, and he will do his best over the next few minutes to answer some of them before we close out today's webinar. Well, Carl, it is looking like you gave such a great webinar. There are no questions. So with that, thank you again so much, Carl, and I spoke too soon.
Here we go. Yeah, so the CO2 injection point, that's what our Scott software handles, which is the kind of storage side of things. I'm not going to be able to speak super in detail about that. But basically that's looking at the formation and looking at where storage might be best, where the storage cost might be best. Yeah, that's kind of handled by a different point. For the test cases, the sink, I chose the point that Heartland Greenway had shown on maps and stuff. And the other point, I just chose a point within the Mount Simon formation, which probably isn't that realistic. But yeah, we have a whole other piece of software that does a lot more to identify those points.
Thank you, Carl. If anybody else has any questions for Carl, please feel free to drop them in the chat. I'll give it another couple seconds here. There we go.
Yeah, so another question, are you able to draw an exclusion zone on the map to tell the software don't route through this area? Or are you able to add buffers around center features to prevent routing too close to a specific feature? Yeah, yeah, we're definitely able to do that. That's something that happens quite a bit. We have exclusion zones built in to our default surface. Like, you can think of things like national parks. We're not going to route a pipeline through a national park. But often when we present routes, people will be like, we don't want a pipeline there, and we'll go through and add in those areas, basically. Yeah. Yeah, it's not another question is this an in-house software or a SaaS that a client could use themselves? Yeah, right now it's in-house. We're running it all in-house. We're moving towards SaaS so other people can kind of play around with it and do what they want to do with it. But Right now it's in-house. Yeah, okay. So Kevin is saying you mentioned you can't really account for routing around landowners that are opposed to pipelines, but it seems you could use outreach, engagement, survey, et cetera, to account for this if the resolution is high enough. What's the spatial resolution of your input data that you showed today? Is it realistic to model at, say, 10-meter resolution? Yeah, the first question, yeah, if you had a survey and you had all the data that said these people are okay with pipelines going through land and these people are not okay, we could definitely put that into the software. That's not something that we often have, right? And for such a broad area, the Heartland Greenway case I was showing is like all of Iowa and then extending beyond that, like that is an impossible amount of land to survey. So if you have those, it's great. We can put them in the software. Often we don't. And we can route. It becomes difficult. We have routed down to 10 meters, and I'm guessing Kevin is planting this question a little bit because we have done that at 10 meters. And yeah, we can get very detailed routes that route like around street blocks and stuff. It gets computationally large. So if you have a super broad network, you kind of have to be realistic about the resolution you're choosing. Because again, the routing algorithm, the Dijkstra's algorithm is really costly to run. And it depends on all the nodes you're using. So if you're at 10 meters, that can be really expensive. But yeah, that's kind of a how broad is our region we're looking at? How detailed do we need to answer? We can play around with those quite a bit. What general parameters does the cost modeling include, and does it include land acquisition costs? So I can go back to the slide that had some of those. Um, we have looked at like property costs using publicly available data. You know, that data is not great often. A lot of these questions just depend on the data. If someone has more detailed land acquisition costs, again, we can put that into the software. It's not hard to add data, it's hard to get data, right? You know, other things we're putting in, you see all the ones atop top the cross there. Um, we've got railways, rivers, roads, slope, kind of federal lands. We've got land use, existing pipeline right of ways. We've got existing transmission line right of ways. We use population density. We also have like some environmental justice and social justice data that we put in. We have worked with people who have used land acquisition costs before. That's something we've done before. But again, it depends on the region you're looking at and the quality of the data that you have.
I will go ahead and give it another couple minutes in case anybody wants to drop another question in the chat. And in the interim, for all of you that joined us today, we do host a webinar generally every month. So feel free to keep an eye on our LinkedIn as well as our newsletter, as we will announce our webinars as they come down the pipeline.
And one other thing a question we get often that's related to land acquisition is, can we minimize the number of landowners that we're negotiating with? That's something we've done also with the software is kind of force it to incur kind of penalties for crossing land borders so you can minimize how many landowners you actually are negotiating with. That's something we've done, but again, that's pretty detailed. You need a pretty good data and you have to be zoomed in pretty close to be able to do that.
Okay, I think we will go ahead and wrap it up here. Again, thank you so much, Carl, for presenting today and for all of you that joined us to watch Carl's webinar. We appreciate it. Feel free to tune in next month.
Thanks, everybody.